Assalamualaikum and hi everyone. We are now going to cover chapter 2, homogeneous semiconductor. For this video, I'm going to cover the semiconductor fundamentals and band structure. I hope you have fully understand the very basic part of a semiconductor that I have covered in the introduction to semiconductor session. We have discussed that a semiconductor is a type of material or a combination of materials that has electrical conductivity value larger than an insulator but smaller than metal, meaning that, as the name goes, the semiconductor can sometimes become an insulator and some other times it can be a metal, or we can say that a semiconductor can conduct current under specific conditions. In this video, we are going to discuss on the semiconductor in order to give you the understanding of semiconductor fundamentals and on the band structure of a semiconductor. The bonding type of a semiconductor is covalent bonding. In covalent bonding, the neighboring atoms share their valence electrons with their neighbors to form a stable configuration. In this figure, the red dots are the electrons that are shared among the neighboring silicon atoms. So you can see that, for example, this silicon atom in the middle share electrons with another 4 neighboring atoms to form a stable configuration, meaning that having 8 electrons at the outermost orbital. The figure showing the atomic bonding is called the bond diagram. The covalent bonding also can be drawn as in this figure. Only the shared electrons are drawn, represented by the black dots. This is also considered as the bond diagram. As I have explained previously, the atoms, when they are very close to one another in the material, the outermost orbital will split into 2 bands or 2 energy levels. The top energy level is the conduction band and the lower one is valence band. Valence band will always be at the lower energy part and closer to the atoms. So the electrons that are in the valence band has lower energy. The top energy level is the conduction band. Only the electrons that have energy that is high enough can be at the conduction band. We then simplify the band diagram without having to draw the atoms near the valence band. The things that are important in the band diagram are the conduction band H, showing the minimum energy value for the conduction band EC, the valence band H, showing the maximum value of valence band energy EV, the y-axis showing the energy and x-axis is showing the location. The highest energy level is known as the vacuum level, EVAC, which can be loosely defined as the energy of a free electron outside the crystal, near the material surface. There are a few other energy-related definitions. Electron affinity is the difference between EVAC to EC, while ionization energy is the distance between EVAC to EV. For a semiconductor and insulator, the conduction band and the valence band is separated and there is a gap in between the two. This gap is known as the energy gap or band gap, or also known as forbidden gap. In the forbidden gap, there is no electron exist. Electrons are forbidden to be in the space, therefore it is called forbidden gap. Then further simplifying the energy band diagram, we only have to draw the EC and EV. Further explaining the band diagram, we already know that the band diagram is showing the EC and EV, and in between EC and EV is the band gap. Thus, band gap can also be defined as the energy that is needed for an electron to be excited from the valence band to the conduction band. Band gap can be calculated using EC minus EV. For example, if the value of Eg is given as 1.12 electron volt, thus for the electron from the valence band here to jump to the conduction band, it needs at least 1.12 electron volt of energy. And the band gap for all materials are unique, which means there are no two materials that has the same Eg value. For a material to conduct current, the electrons must be at the conduction band. Although there are a lot of electrons at the valence band, but the electrons at the valence band are closely tied to the atoms. Thus, they are not freely moving. The electrons must be at the conduction band to move freely, thus are able to conduct current. Since the band gap is the energy that is needed by the electrons to jump from the valence band to the conduction band, the value of the band gap determines the electrical conductivity of the materials. Thus, as can be seen here, the insulator has the widest band gap among these three. This means that the electrons need very high energy to jump from the valence band to the conduction band. And most likely, even if we give external energy to the insulator, the energy is not enough. Thus, there will be almost no electrons at the insulator's conduction band, so the insulator cannot conduct current. Comparing insulator to the semiconductor, the energy gap of the semiconductor is smaller. This means the energy needed for the electrons in a semiconductor to move from valence band to the conduction band is less than that of an insulator. This narrower gap allows external supply of energy to provide the electrons enough energy to jump to the conduction band. Thus, under some condition, such as with an applied bias or voltage, the semiconductor can conduct current. Finally, the metal, as can be seen here, the conduction band and valence band are overlapping. So there are always electrons at the conduction band, and thus metals always conduct current. Band gap not only classify insulators, semiconductors, and metals. Band gap also classify the characteristics among the semiconductors. The conductivity of a semiconductor is defined by the width of the energy gap. For example, gallium arsenide has an Eg of 1.42 electron volt, silicon 1.12 electron volt, and germanium 0.66 electron volt. From these three examples, the germanium has the narrowest band gap, meaning that among these three, germanium is the most conductive. This means germanium needs only a low voltage to turn it into a conductor. Or in other words, if germanium is used as a transistor, it needs only low voltage to turn it on compared to silicon and gallium arsenide. Finally, in a semiconductor, there are two types of current carriers. One is electron and another is hole. Electrons and holes are carriers means that the movement of electrons and holes in a semiconductor determines the conductivity or the electrical characteristics of a semiconductor. The electrons must be at the conduction band to conduct current, and holes must be at the valence band to conduct current. To summarize, the atomic bonding in a semiconductor is covalent bonding, in which the neighboring atoms share electrons to achieve stable configuration. The conductivity of a material can be defined by the energy gap. Insulator has the widest energy gap and metal has no energy gap. Semiconductor has an energy gap that is smaller than an insulator. Thus, it can conduct current under certain conditions. In order to conduct current, electrons must be at the conduction band and holes must be at the valence band. These are called carriers.